Good morning, everyone. Our chapter today is about particle size analysis. First, we need to know why particle size is important. By reducing particle size, the solution rate will be more because reducing particle size will increase surface area of contact between particle and the surrounding the solution medium, so the solution rate will increase and also solubility will increase. On the other hand, if you are making a suspension, it's better to have a suspension with a small particle size rather than coarse powder. Because if you have coarse powder, sedimentation rate will be very fast and the patient will not have enough time to take the dose after shaking. The third point is about uniform distribution. Again, if you are mixing two mixture or two material, one of them having coarse powder and the other is having very fine powder. After mixing, like coarse sugar and fine sugar, after mixing there is a possibility, great possibility of segregation. If you did any vibration or transfer the mixture from one place to the other, the fine powder will move upward by gravity and the coarse powder will move downward also by gravity by their heavy weight. So it's better to have uniform size. Either the two components will have the same size, the same small size or even the same coarse size, but not different. Another point also, if you are making a transdermal gel or transdermal cream, if this gel or cream have nanoparticle inside, it will be better for absorption through the skin. But if you have coarse powder, the coarse powder will struggle to pass through the skin layer and it will be impossible. Again, even if this gel or cream is topical, acting only on the skin, local action, so having also fine powder is better because it will decrease greatness and irritation to the skin. We have different ranges of or categories of particle size. The particle may be very coarse, moderate, fine, or very fine. But this classification is very vague, not objective. It's better, of course, to express the particle size by certain number, like 100 nanometer, 500 micrometer, and so on. So we have in this chapter about four methods of measuring particle size. First one is sieving, which is the simplest one. Second one is microscopy, sedimentation rate method, and stream scanning. We will start with the simplest one, which is sieving. To make sieving, you should have a set of sieves arranged in descending order regarding the opening size. So the sieve with the largest opening will be kept on top, and the sieve with the smallest opening will be kept in the bottom. And you will have a mixture of powder with different size that you want to measure or analyze their sizes. For example, 10 gram mixture, and you will add this 10 gram mixture on the first sieve, then you will start shaking. After shaking, of course, the very fine powder will pass through all sieve and kept on the smallest sieve in the bottom. And the very coarse powder will be kept on top on the first one. And the intermediate powder with intermediate size will be kept in between in the second and third and fourth sieve and so on, based on size. So you can take the weight or measure the weight kept on each sieve. So based on that, for example, if on the first sieve, if 1 gram is kept, so it's 1 gram out of 10 gram mixture. So it means that we have 10% of the powder having this size. And if you have, for example, 0.5 gram kept on the smallest sieve, it means 0.5 gram out of 10 gram means 5%. 5% of the mixture are very fine, and so on. And any fraction also in between, you can measure the percentage retained. And then we can plot a graph between particle size range on the x-axis and percentage retained on the y-axis. The advantage of this method is simplicity of technique and simplicity of equipment. Regarding equipment, you need only set of sieves, which is very cheap and very simple and available. Regarding the technique, you need only shaking of the set of sieves so the powder can move between the sieves based on their size. But again, it has some disadvantage. It requires large sample size. I said before it is 10 gram, but 10 gram for some drugs is very large. Because if you have anti-cancer drug and this anti-cancer, 1 gram may cost thousands of dollars. So having a 10 gram is something huge for some active ingredient. Another point is micrometer range and nanometer range. all the sieves are in micrometer range or bigger than that. There is no sieves having opening with the nano range. So if you have nano powder in between, you cannot detect, you cannot classify, and you cannot make a graph having a column in the nano range, for example, between 100 nanometer and 200 nanometer. So if you have nano, you should have other method other than sieving. So that's why the second method is microscopy. Microscopy is very important because microscope can detect the size and also can detect the shape of the particle. If it is spherical or irregular, but not only size and shape, the characteristic of the surface, like if the surface is smooth or not smooth, or porous or non-porous, and so on. All these characteristics are very important for new active ingredient. Before starting the measuring the particle size by microscopy, you need to prepare your sample. You have to take a sample from the material, take a sample of the powder, and suspend it in suitable solvent. And the word suspended, it means you have to select a solvent that cannot dissolve the powder. Because if the powder dissolves in the solvent, you cannot see anything under the microscope. You will see only clear solution. That's why if your powder is water soluble, you have to suspend it in oil, like mineral oil or liquid paraffin. And if your powder is oil soluble, you have to suspend it in water. After preparation of the sample, you should put it under the microscope on slide and use the suitable lens, either 10 or 40 based on the magnification that you need. And this microscope should be connected also to a desktop or laptop where there is a software transferring the picture to your screen, and you can use your mouse just to draw a line, very simple, just to draw a line inside each particle. So the software, based on the magnification, will show you the size of this particle, will write digitally as a number like 200 micrometer, 100 micrometer, will show you the size of your particle. But of course you have to repeat that several times to take the average, and also the software will calculate the average automatically. The disadvantage of this method, you cannot measure the size of single particle. You have to take a sample of 1,000 particle at least. So you have to draw lines 1,000 times for each sample. It means it is very tedious and time consuming, and also at the same time, it's not suitable for nanoparticle. All that are done for microparticle down to 1 micrometer, not less than that. That's why we have, for the nano range, we have more advanced microscope, two types of microscope, transmission electron microscope and scanning electron microscope, with abbreviation TEM for transmission and SEM for scanning. The range of size, both of them can be used for nano, but the ideal for nano again is transmission, because it's very sensitive and very accurate for measuring the size between 1 nanometer and 1,000 nanometer, which it means the whole nano range. While scanning electron microscope, it has a part in the nanoparticle and another part in the microparticle. It can be used for both, but not the very small nanoparticle. It starts from 100 nanometer to 1,000 micrometer. Regarding the advantage and disadvantage of scanning and transmission electron microscope, both of them, of course, can be used for nanopowder, starting from 1 nanometer for transmission electron microscope, and starting from 100 nanometer for scanning electron microscope. The other advantage, which is not present in any method before, is surface characteristics. Through the picture, you can see if the surface is porous or non-porous, smooth or irregular surface, and so on. And that is very important for us, because if the surface is porous, it will give an indication about the solution rate, for example, and solubility. Because if the surface is porous, the solution medium can easily penetrate inside the particle and dissolve it immediately. But the disadvantage, it is very expensive. The transmission or scanning, both of them are huge equipment and still expensive. Not all research labs can have the same equipment. The other problem is time consumption. To prepare your sample, you have to coat it with certain material. In case of transmission electron microscope, you have to coat your sample with carbon, which take about half an hour or 1 hour for each sample. The same also for scanning electron microscope. The sample should be coated by gold, which is again expensive and again time consuming. And also during coating, there is a certain degree of overheating. Maybe the temperature may reach 40 or 50 degree during coating, especially coating with gold. Some samples are having lipid, cetyl alcohol, for example, which melt at temperature 40 or 45. So the sample itself may melt, and if the sample melt, of course, you cannot measure any size because all particles will fuse together. The third method is sedimentation rate, which is very simple. If you have a suspension, just shake the suspension and allow the particle to settle down, to sediment. And using a stopwatch, you can measure the time taken for sedimentation. If you look at the equation, Stokes law equation, dst equals square root of 18 eta h over rho s minus rho node times gt. Of course, eta is the viscosity of the medium, viscosity of the liquid itself. Rho s is the density of the solid suspended in water, and rho node density of the dispersion medium, which is mostly water, and g acceleration due to gravity. So the remaining thing is h and t and dst. T is the time taken for the powder to go down to a certain distance. If the powder went down like 5 centimeter within 15 minutes, so time is 15 minutes, and h, or the distance, is 15 centimeter. And if you know h and t, you can calculate, of course, dst, the diameter. So again, another example, if you have your suspension after shaking, you will observe it for certain seconds or minutes. If the sedimentation happen through a certain distance, this distance is about 10 centimeter within 3 minutes, so the time will be 3 and the distance will be 10 centimeter. So that you can use the equation to calculate the diameter of the particle. The other method number 4 is about stream scanning. And stream scanning here is happening by two techniques, either by electrical conductance. We have an equipment called Coulter counter, and another technique is about laser light scattering. Based on the scattering of laser light, we can detect the size. And we have two sub-techniques here also, which are static laser light scattering and dynamic laser light scattering, and we will take example of each. The first example is Coulter counter. Coulter counter depends on having a positive and negative electrode, and these electrodes are dipped inside electrolyte solution like sodium chloride. So the ions of sodium chloride will connect or will conduct the electricity between the positive and negative electrodes, and this conductivity is measured here in the middle in the yellow circle. So without any suspension, without any particle, there is a conductivity moving in between the positive and negative electrode, and this electricity is measured in between inside the yellow circle. If you add your suspension, which is having here a green color, and your powder will start moving through the liquid or through the electrolyte solution, once any particle move in between the yellow circle, it will decrease conductivity. It will act as an isolator. And the decrease in conductivity is directly proportional to the particle size. It means if your size is bigger, the decrease in conductivity will be more. Conductivity will decrease from 100, for example, to 20 if your size is big. If your size is small, conductivity will decrease from 100 to 80. If your size is very small, conductivity will decrease from 100 to 95, and so on. So the software of the equipment itself can convert the decrease in conductivity into a particle size by certain equation or by certain technique. The next technique, which is the most advanced technique to measure the particle size, is dynamic light scattering or photon correlation spectroscopy, or the most common name is zeta sizer. This technique is mainly used for nanopowder, and you will understand why, especially for nanopowder. And in this technique also we have laser light source here on the picture on the left side, and we have a detector here in the middle, so you can detect the intensity of the laser light anytime. In between you will have your particle suspended in water. So if your nanoparticle are present in between the source and detector, it will affect the intensity of laser line detected by the detector. But the idea, these nanoparticles are not static. Nanoparticles are always moving or vibrating in a random motion called Brownian motion. This Brownian motion comes from the collision between the nanoparticles and the dissolved molecules present in the solution. Any solution is having dissolved molecules, whatever the molecules, and these molecules are very energetic, so it dissolves, it is soluble. Due to this high energy, it will continue to move in a random Brownian motion. Once it moves, it will collide or hit the nanoparticle. So the nanoparticle itself also will start to move in the same or similar random motion. And if your nanoparticle are moving in a random motion up and down, it will affect the laser light detected in the detector. So the laser light intensity will go up and down very fast. And the change in the laser light scattering depend on the motion of the particle. If the particle is smaller and smaller, it will move faster and faster. So the change in the laser intensity will be faster. The line will go up and down very fast. If your nanoparticle is little bigger, like 500 nanometer, 700 nanometer, so it will move in random motion, in Brownian motion, but slowly. So the laser light intensity will change up and down, but slowly. And the equipment itself, again, has a software to integrate or to change this change in laser light intensity into a particle size using certain equation. This equation is D equal K T over 3 by eta dB. A very simple equation integrated inside the equipment. K is a constant, Boltzmann constant. T is temperature in Kelvin, because temperature will affect, of course, the energy and the movement and everything. Eta is the viscosity of the liquid, because again, if the liquid is more viscous, it will affect the movement, the Brownian movement. And pi, of course, is a constant. And D is the diameter. dB is the diameter of the particle, and the d capital on the left side is the speed of Brownian motion. So there is an inverse relation between the diameter, which is dB, and the capital D on the left side, which is the speed of Brownian motion. To understand more, here we have two examples. One example on top for large nanoparticle and the other one for a smaller nanoparticle. If you have a larger nanoparticle and there is a collision between the larger nanoparticles and the molecules, which is having a light blue color in this picture, the nanoparticle, the larger nanoparticle like 500 or 700 nanometer, as we said before, will move up and down in random motion, but slowly. So the change in intensity will be also slow. The curve will go, the red line will go up and down slowly, as you see on the top right side. The other example for a smaller particle, if you have nanopowder with size 50 nanometer, 10 nanometer, 20 nanometer, collision will be more, movement will be faster because the particle is lighter. So the change in light intensity detected at the detector site will be faster also. So the line will go up and down very fast. And again, the software will convert this change in laser intensity into a particle size. So again and again, if you have a smaller nanoparticle, you will have a fast Brownian movement, fast fluctuation in laser light intensity. While if you have larger nanoparticle, Brownian movement will be slower, and you will have a slower fluctuation in laser light intensity. The advantage of photon correlation spectroscopy or zeta sizer, very fast, very rapid, no need for sample preparation, just you can put the suspension in a cuvette, in certain cuvette, and keep it inside the equipment. Within 1 minute, you can measure the size, and very accurate also, because no need here to measure the size of particle one by one. It's stream scanning, it's continuous, so it can measure the thousands of particles within no time. The disadvantage of stream scanning, it didn't give any idea about the characteristics of the surface and the shape of the surface. The last title in this chapter is about particle size distribution, and we have to differentiate between particle size and particle size distribution. Whatever we finished till now in this chapter is about measurement of particle size. Particle size may be 100 nanometer, but the particle range may the particle may range from 1 nanometer to 1,000 or 10,000 nanometer. So there is a great variability in size. Like curve B. Curve B, the average is 16, but here the curve is very wide. So it means there is a great variability in size. While if you look at curve A, it has the same mean, same average particle size, but it has less variability in size. The range usually or in curve A start from 15.8 to 16.2. So we need something to express the variation in particle size. What we have here in this chapter is body dispersity index. Body dispersity index is a number ranging between 0 to 1. If body dispersity index is less than 0.1, it means that your dispersion or nanosuspension is monodisperse. Monodisperse, again, it means that all the particles are having the same size without any variation, which is ideal. But if your BDI or body dispersity index is more than 0.7, it means that your nanosuspension is highly body dispersed. There is a great variation in particle size. Even if the average size is ideal, 10 nanometer, but the range is very wide, starting from 1 nanometer to 1,000 micrometer, maybe. And in between 0.1 and 0.7, it means that your dispersion is body dispersed, may be acceptable or not acceptable based on your work and your target for use of this nano suspension. Of course, the smaller the better. If it is 0.2, better than 0.3, better than 0.4, and so on. And it can be calculated by a simple equation just by dividing the standard deviation of the size over the mean diameter size all square, and that is how we can calculate the BDI. So as a summary for this chapter, we have learned how to measure the particle size by different techniques, starting from sieving and microscopy, the simple microscope, light microscope, and then transmission and the scanning electron microscope. Then we went to the level of stream scanning using Coulter counter, which is mainly used for microparticle. And then also we mentioned that Zetasizer, which is the most advanced, the most important equipment in this chapter, used for measurement of the size of the nanoparticle. And then we took a small part about body dispersity index and the variation in particle size. Thank you so much.